So I'm really excited to welcome on stage Jan Jongboom, CTO and co-founder of Edge Impulse. Woo!
Cheers, guys. Brilliant decision, not putting my tech keynote right after Zach so everyone would leave by lunch, but actually, and open the bar at 3:30, like really great from the event organizers. I'm Jan. It's been truly tremendous, not just seeing everyone here. Like I couldn't make it last year because I couldn't enter the country, unfortunately, due to COVID. So this is truly the first real event that we throw. Like how truly amazing this is. And not just the people here, right? But the community, the people watching on the live stream right now, the people who are going to watch this on YouTube. And the thing that I'm most proud of, like, I think a really big compliment that we got from some people just in the break, they said, well, we always complain that there's not enough end customers at all of these events. And now they were complaining that there were too many end customers and we need more technical content. So let's balance it out. So first of all, let's go reflect a little bit on what happened in the past 12 months. So some numbers. So this was Imagine 2021. And this is our project count. So Zach already touched upon it in his keynote. So during Imagine 2021, we had 36,000 ML projects being created on Edge Impulse, which is already an astonishing number. If you would have thought me that 3 years ago, I wouldn't have believed you. But then look at the ramp of this peak. And this whole graph is since the inception of Edge Impulse, the launch of Edge Impulse back in January 2020. We're now at 115,000 projects. It's holy shit. Holy shit. This is amazing. We have, yes, thank you. And there's 300 new projects being created every day. Truly astonishing. Over the past 12 months, we ran 229,000 hours of compute. That you might not realize like how much that is, but that translates to an AWS bill of about $600,000. We have 20 jobs running in parallel at every moment, every day. Truly insane. We have 60 million data samples that were added in the past 12 months. And then you realize as well, like collecting data is hard work. But still, we've managed, these 60,000 new projects have managed to create 60 million new data samples. So that's people actually going into the wild and actually collecting stuff from real devices. It's really insane. And our dev team, we have not been sitting quietly. We have been working very hard as well. We have over 2,000 commits to master. And in the talk that we have today, I'm going to highlight a couple of the new features that we've been building over the past 12 months, and a small look forward into the new stuff that we're going to release very, very soon. So what we like to say when we go in with a new customer is that everything always starts with data. I think, in all fairness, Edge Impulse is not a machine learning startup. We help you get information from data startup. And machine learning is one of the techniques that we use to do that. But if you do data-driven engineering, so you use data to make those decisions, then having high quality and good data and representative data, that's kind of where everything starts. So what we released back in April is, I think, one of the best additions that we've made to the Edge Impulse Studio in basically since the start. And this is something that came out of the work that we did with Vijay Reddy's group at Harvard. And it's a data explorer. So it's a one-view overview of your complete data set, but not using traditional dimensionality reduction algorithms. Rather, we use a neural network to generate neural network embeddings. And those embeddings we then visualize in a 2D plot. And what that does is that it gives you a debug view of the neural network. So by just throwing your data set in here, and this is common voice, we can very quickly see junk samples, stuff that is mislabeled. And in addition, what we can do is that we can very quickly label unlabeled data. And we just do that by just throwing unlabeled data in and see where it lands. Maybe it's a new cluster, maybe it falls into one of the existing clusters. And this helps so much. Like if you look at why, for example, in MLPerf, the visual wake word detection, like the maximum you can get is 89%, it's just because the data set is shit. There's all kinds of stuff in that data set that are not person. The Data Explorer has been a tremendous help in just identifying those samples and getting rid of them. So really awesome stuff. The second thing that we've shipped is data sources. So data sources allow you to integrate with your cloud provider with a single click of a button. So you have your data, your camera is feeding data to S3, click a button, we'll automatically get that data into your project, and then we run that as part of a pipeline. So we can run it daily, we can run transformations over that data, and we can set up new rules. So stuff like, I want to retrain my model after new data has been added. Version this. And then if my accuracy didn't drop, send me a notification, build me a binary, and send me a notification to my device management service, so you just push a new firmware update directly to your devices. The two things together, so data source and data explorer, allow you to also do some assisted labeling and active learning, what Zach already mentioned. So the data explorer uses neural network embeddings, and that gets better over time. So the more data you add, the better those embeddings become, because they start separating this data. Then if we get new data showing up, if it's in a cluster that you already know, awesome, just auto-label that as the right data. But now you can get kind of the interesting samples that come in, stuff that falls outside of a cluster or falls in the middle. That's the stuff that we allow you to label, and that reduces labeling time by 90% on projects that we've seen. And together, all of that enables active learning. So active learning is like, I'd like to say, machine learning is not a one-off, right? It's something where you continuously learn. The best customers that we have, not in terms of money, but in terms of like how much they use the product and how much value they get out of it, have nailed this down. It's a continuous process where you get data from your edge device, you collect it, you label it, you retrain your model, you verify that accuracy didn't drop, and then you deploy back. So the learnings that we've done around active learning, data explorer, data sources, transformations, etc., have all come together in our health reference design that Zach said. So this is an end-to-end design on actually showing how we deal with clinical data, how we do data collection from that, and then in the end, deploy that in Omnivise ML. There's a couple of really cool kind of tricks in there that we've learned from working with Aura, No Labs, and No Watch, customers in the health space. For example, if you work with multiple devices, you realize, if you think about working with a single device and how hard it is to get data from that, now try doing that from 3 devices in a clinical setting and then trying to align all of them. So we've added something called checklists. It's a super low-tech way, low-tech solution, but really useful for data Q&A engineering. So just stuff like, hey, do we have actually all the files? Do the time zones match? Like very simple Q&A checks. Already been a tremendous help. Like talk to Jura from Aura if you want someone to attest to that. And we've been working on some stuff around finding correlation between data. So think that you're in a sleep lab and you're sleeping with the ECG and EEG pads, on your body, and you're sleeping with an Aura ring on both of your hands. How do you know that the data you get from the ECG and EEG reading actually match the ring? So you might think, well, someone types an identifier for that person in. OK, awesome, yeah, sure, that works. But data errors are being made. So stuff that we do now is things like correlation finding. So we try to see if, for example, on the heart rate channel or on the activity channel, do we have peaks at the same time? If not, then that's a really good indication that you're not looking at the right data. And if you don't catch this stuff early, your data set is going to be screwed. And in addition, what we can do, so you see these peaks are the same, but they don't completely align, is do stuff like time synchronization over this. Truly useful and an absolute must if you do this stuff in a clinical setting. So we ship that. Now the second thing is like right after we say everything starts with data, is that the customer says, well, but I don't have any data, right? And it's really hard to collect. And it's not really the customer's fault or anything. It's a problem that we have in general is that there's a lot of data set asymmetry. So you typically have lots and lots of good data, like normal operation. You have a machine, and the machine mostly functions correctly. And then maybe, if you're lucky, you have a few samples of incorrect data, fault data. And that fault data is typically not even just like one class. It's actually split between multiple classes, right? You have fault state 1 and fault state 2 and fault state 3. So you have even less data per class. And then very often, there's also fault state that you don't even know anything about. Even harder. So how do we deal with that? So traditionally, this is one of the first things we built, actually, when we started at Jimples, was to add some safety guards through anomaly detection. So what we do here is that we say, well, this is the complete potential input space that you have, all the potential inputs that can go into your model. And then we do a learned representation of just the training data. And now when we have new data coming in, we just look where this falls. So here is some data sample that fits nicely in those clusters. It doesn't mean that we've seen this training sample, but that it looks similar to the stuff that you have in your training set. So we say, OK, in this case, we haven't seen this input. This is not an anomaly. But when something falls outside of that cluster, we say, hey, this is an anomaly. Either we don't trust the neural network for the classification, because this is stuff that we've never seen before, or we tag this as an anomaly and ship that off. So the way that we do that today, because this, as said, this has been in EdgeImpulse from basically July 2019, when it was just me and Zach, and all of EdgeImpulse ran on my laptop, is that we take your input, we run your feature extractor, so your DSP code over it, and then we run a clustering algorithm. And that's really nice, because then we have clusters, and data either falls in a cluster or outside of a cluster. Clear. The downside of this is that this requires some feature engineering. So we can train this clustering algorithm, for example, on a rotating fan, on, hey, we always know, because we have our feature analyzer here, we know that for normal behavior, we see a peak at 36 Hertz, and then a secondary peak at 24 Hertz. So we train on that. What happens then if that peak gets lower at 36 Hertz, or it changes because there's a blockade or something, then we know there's an anomaly. And that works really well if you can reason about the data that way. But for a lot of data, like audio and images, this doesn't fly, right? I can't train an anomaly detection model and say, if the pixel on row 7, column 8 is red, then there's definitely an anomaly. That's just not how image classification works. So our second version of anomaly detection is going to look like this. We still have the input. We still have DSP features. Still, like, as long as you can avoid doing anything with machine learning, great. That's one less problem to worry about. I love signal processing. But now, similar to what we do with the Data Explorer, is that we'll be using neural network embeddings, sort of a debug view of the network. So we cut your neural network off here, and then we combine it with a Gaussian mixture model. So this gives you the Gaussian distribution of normal inputs as seen by the neural network, and that's what we train our anomaly detection methods on. And this is super cool, because what this gives us is a flexible addition to any neural network, where we can convert any classifier that you have today into something that can detect anomalies, sometimes even at the same time. So you might have one network, so one amount of compute, and at the end you have a classifier head and an anomaly detection head, basically for free. And this finally solves this issue that I think everyone has seen, where you have a classifier, and the classifier can detect these 10 image classes that you've added really, really well, but then you put something in front of it that is never seen before, and now it just gives random results. So this is a really cool addition, I think, here. So I have an example of how this works. So FOMO, faster objects, more objects. The acronym came first, and works essentially like this. So it's a neural network that outputs a heat map. So every cell here essentially acts as a classifier. So this is the result. So if we train this on Jenga blocks, all of these cells will activate. And from that, we can then derive the centroid of the object, or draw a box around it, or whatever we want in a post-processing step. Now, as said, our new anomaly detection work is an add-on to any neural network. So what we can do with Fomo AD, so Fomo for anomaly detection, is that we remove that classification head and rather attach a Gaussian mixture model at the end. And now, rather than every cell is a classifier, every cell is an anomaly detector. Now, what does this give you? This gives you a situation where you just need to provide normal data, so data that you expect this camera to see. We train on that. We train on patches of that. And after that, you feed it through. And then we'll tell you for each cell, do we think there's an anomalous item in here, yes or no? The truly insane part is that there's almost zero overhead, right? There's just the overhead of the inference on the GMM side, but that's very, very tiny. So this runs with the same performance as Fomo today. So up to 30 frames per second on a Cortex-M7, and up to 200 frames per second on like special accelerators. And because Fomo is completely convolutional, you can also, if you have enough memory, you can throw really big images in, and we'll find even the smallest of defects, which is really cool. So here's a demo. So this is on the Ready Robotics robot arm. We shot this 2 days ago in the office. So the camera is actually on the arm at this point. And you see a view of the camera here. And the darker a cell, the less anomalous it is. So we've trained this on background image, so the blue overview that you see here and the blocks. That's normal data. And let's go run it. So it's moving around, that's fine. And now we introduce a red cube, and it just lights up. And the image state goes to anomalous. So we know that there's an anomaly, there's something in there that shouldn't be there, and we know where it is. Remove it, goes back. We add a large green object here. Immediately lights up. That is definitely an anomaly here. And we can use it for safety features too. So if Arun puts his hand there, immediate response. So up to 200 frames a second, this on embedded Linux. Flawless and only trained on 100 images. It's really insane. And we can do all the stuff that we can do to make more with less data, like transfer learning, model architectures, etc. we can do with Fomo AD. And this is not just going to come to visual data, but it's also going to come to audio data, and later also to sensor data. So first Fomo AD, probably early 2023, available, and then the rest of this stuff comes. I think super, super exciting. Then something that Zach also alluded to, which is that every device is sort of similar, but it's also different. So think of the the robot arm, right? As Zach said, we had to recalibrate it because we moved it from the ground floor to the first floor, second floor, whatever you say here in the US, this floor. And that's something that you're going to see in a lot of devices, right? There's a generic anomaly detection model that will probably work for all of these models. So if someone hits it, or it grabs your finger, or tries to move a chess piece, and then have you seen that video? No. So that's your generic algorithm. But then for this specific device, there's stuff that is normal for this device that is abnormal for other devices, and the other way around. Think of it, let's say that you're normally just picking up small pieces of wood, and all of a sudden you pick up something very heavy and you have a lot more stress in your joints. Not anomalous in general, but anomalous for that machine. So how can we fix that? So we have been working on a tool called on-device calibration. And on-device calibration is something that runs completely local. So this runs on the chip itself. It can run, depending on the complexity of your model, even on MCUs. It will take in a complete anomaly detection pipeline. And then we learn in this Gaussian distribution what is normal for that specific device. So it's not a magic button. It's not a device that you put on any random machine and it will figure out anomalies. It still requires careful engineering. That's why we don't call it on-device learning, but rather on-device calibration. But after that, it's really powerful. And I have a demo for that as well. Shot this morning from my hotel room. So in here I have a device, and it's trained on our Edge Impulse 101 demo, which is the continuous gestures. So this device can recognize idle on my desk, up and down, waving, and snake. Now, for this specific device, the only thing that's normal is going to be idle and up and down. So I'm in calibration mode now. So it's getting normal data. I'm just going to show what is normal. So here, up and down is normal. And after about 70 samples, I press the button. And then we go into training mode, or calibration mode. There we go. So this ran locally on Cortex-M4. And now it's in anomaly detection mode. So as long as we do stuff that it's seen before, completely normal. But now we do something that's in the training set, but not here on the device, like waving, immediately gets flagged as an anomaly. So truly, truly, truly amazing. Like this, what we can now do with all of this is just do stuff with only normal data. We have devices that can actually accurately detect anomalies, both in audio, both in vision, and in complex sensor data, and do on-device calibration. Like, if a customer now still says to me, like, I don't have enough data, now I really don't believe them anymore. All right, so that was lots of data. Let's talk about ML models. So at Impulse, like, we have an amazing tech team, but we're 65 people only, right? Out of 7 billion people on the Earth, that's not a lot. So while we can build tons and tons of models, we can't build everything, right? Like, we have really cool stuff. We have Fomo, we'll have Fomo AD, we have few-shot keyword spotting, mobile nets. If you want to modify something in Edge Impulse, you say, hey, I want to do something a little bit different. Cool. We have an expert mode for that. You click the button, you get, Keras API. But there's a lot more. There's a lot more stuff outside of the world, right? The world is much bigger than just what we can build internally. So there's novel architectures, YOLO v5, efficient net. Maybe you want to do some custom transfer learning because you're Conservation X Labs and you want to have a cool transfer learning model for your customers. Maybe you're a silicon vendor, right? And you have YOLO v5, but you actually swap out a couple of layers because that makes it run faster in your silicon. We can't do everything ourselves. Maybe you have completely novel architectures that you built internally with your data science team. So you just write that in PyTorch, Keras, or scikit-learn. And maybe you want to do experimentation, right, that you can't do in Edge Impulse. We have the weights and biases folks over here. They're going to talk about this just later. Maybe you want to find the optimal number of convolutional layers in the middle of your network. Maybe you want to do some new data augmentation. Like, this is all stuff that we can't provide for you. So how are we going to fix that? Bring your own model. I couldn't, BYOM. It's a little bit less good of an acronym than FOMO, but it'll have to do. So bring your own model is live today for everyone. So this is actually a feature that we had for enterprise customers for a while. We've opened it up for every developer now. So it's a complete toolkit to take any model, whether it's trained in PyTorch, Keras, scikit-learn, TensorFlow, and we have examples of YOLO v5 and EfficientNet as part of this as well, and bring them into Edge Impulse, and it'll show up exactly like any other model in Edge Impulse. This is really cool, because what it allows you to do is that it allows you to have your ML engineer be a ton more productive. There's all kinds of shit in a real ML product, in a real ML pipeline, that your ML engineers don't want to deal with. Stuff like getting data from devices, time synchronizing these data, doing Q&A checks, etc. What your ML engineer would appreciate is just a clean stream of already verified data. So that's what we're going to give you, right? We're going to let your ML team add value where they add value, which is on this experimentation and modeling side. So some stuff to be released here is new CLI tooling to quickly get updated data. So just one command, bam, you have your data already in NumPy format, already nicely spread out. You just go do your ML on top of it. We now ship a new Python SDK where you can locally give us a model and we'll tell you how fast it's going to run on real hardware and give you accurate RAM and ROM numbers. And this is amazing. Like if your ML engineer is tracking something in weights and biases, you want to know the complexity and the number of ops in the model, you want to know the accuracy and the F1 score, but now you can also track how much RAM this is going to take on device. So if you're running a sweep in weights and biases, for example, and you see, hey, actually this is more than 100K of RAM, that's something I don't have on my device, awesome. I just eliminate that straight away. I don't even want to go explore models in this direction. We will handle, as we always do, compilation and deployment. Like you have heard, if you were in the Lightning talks, you heard from so many silicon vendors that built truly amazing new silicon, new accelerators, new NPUs, GPU combinations. All of that is supported in Edge Impulse. We'll handle that deployment step for you. So if you're an ML engineer, you say, hey, cool, I want to deploy to a super wide ecosystem of devices. Awesome. Push it to Edge Impulse. We'll handle all of that for you. And we'll host the pipelines for you. And that is interesting because who likes to get a text on Slack saying, hey, we have some new data. Can you retrain this model for me? Right? Really annoying. But we just host it in the pipeline. You push it once. And this comes with the whole retrain pipeline as well. So there's new data. We'll retrain it for you. We'll host these models. We'll make sure that no dependencies break. And then you can deploy. So completely integrated in all the stuff that we do. All right. So that was the three main topics. Then there's a couple of new releases that I want to touch upon. And all of these are live today. So our EM compiler. So it's our neural network compiler for MCU-level devices. We've been porting a whole bunch of new kernels here, and that's because we are supporting Bring Your Own Model. And there's a lot of stuff, a lot of kernels, a lot of operators, etc., that are in here that are not supported right now in TensorFlow from microcontrollers. So, for example, because we now add scikit-learn support, and thus classical ML algorithms that you can port easily, there's a ton of operations happening in there that are not happening in typical neural networks. So silicon vendors have not ported that. What we have done is that we now implement software kernels for all of those. These are in our SDK. And silicon vendors can now come in and provide hardware-accelerated kernels for this stuff. So you can do hardware acceleration on classical ML algorithms as well. As part of that, we also are working on one of the coolest technologies that I have ever seen, which is called JAX. And JAX is, in essence, it's a Python to graph compiler. And from that graph, you can then go through a compilation step to TensorFlow. And from TensorFlow through Eon, we can go to source code. So what this gives you is that you can write Python code, vectorized Python code, and we'll handle the complete compilation step to run this efficiently on embedded systems. So we've been implementing this as part of our work to enable scikit-learn, but we're going to go one step further, and that is that we're going to allow you to write signal processing code in the same way. So you write a signal processing block, you do your FFTs, you do your matrix multiplications, you do your filter banks. You write it in Python once, we'll handle the compilation, we'll handle the hardware optimization, we'll handle the quantization, and get that running on device for everyone. I'm going to go talk more about this on Friday at 9:15 a.m. Pacific. Then we're going to go into a demo. But all of this is live, so if you go to bring your own model and you click on the scikit-learn example, you'll see exactly how we've done that. And in addition, we shipped the latest release, which actually uses between 5 and 8K less flash. So that's really great for smaller models. So especially if you think about something like the gesture model that we had just now, that used to take 40 kilobytes with TensorFlow Micro, 20K with Eon, and now it takes about 13. So even down a lot more. The second thing is that we have just released, and I think Matthijs, I don't know, I can't see him because of all the lights. So there's Matthijs, the chief architect of the Eon Tuner. We've released a new version of the Eon Tuner, our AutoML pipeline. So the Eon Tuner finds the best model within the constraints of your device. So we are hardware aware. So you want to run this on, hardware from silicon provider A. You have 26 kilobytes of RAM available still, and you have a hard latency target of 100 milliseconds. Awesome. We'll go find the best model within that search space. Previously, we had sort of recipes. So you said, I want to do a keyword spotting model, and we'll go through all of our keyword spotting algorithms. Now you can do search space customization. So you say, hey, actually, the dropout layer at the end of my keyword spotting model, I don't really know what it's going to be, but anywhere between 0.1 and 0.4. OK, just type that in, and we'll figure it out for you. In addition, to support bring your own model, we'll also support new custom DSP and custom ML blocks. So if you have something you want to test out, for a long time, one of the demo applications that we had in Jimples was one to distinguish Matthijs' cats. And he has 4 cats. 2 of them look super alike, and 2 others also look super alike. So with MobileNet v2, one of the default architectures, we only managed to get to 92% accuracy in the test set. But Matthijs brought in, through Bring Your Own Model, all of the EfficientNet models, ran the Eon Tuner over it, and we managed to get to 98.9% accuracy through that automatically. Like super, super cool. So this is available today. There are some limitations for free users, but enterprise users have full freedom in modifying that and full search space customization. So even if you want to run 1,000 different models through here, awesome. Just set that up, click the button, and we'll make sure to run that for you. The last thing here is performance calibration. So what would it, if I have 95% accuracy in my test set, is that enough for me to deploy this in a performance critical situation? Like, I don't know, right? Because this doesn't tell me anything. Your test set is already really highly curated, right? You probably cut off stuff that looks sounds very similar to stuff that you have. So performance calibration gives you honest insight in what the performance of your model is. And it does that by allowing you to upload a really long, in this case we launched it for audio first, but a really long audio sample, let's say a day, right, 24 hours, annotated with, for example, the keywords that you want to detect or the audible events that you want to detect. We'll run your model over that complete day of data, and then we'll plot you the false activation rate and the false reject rate. So how often did the model spuriously activate, and how many times did it miss an event? Now then we actually have about 200 different post-processing parameters, like maybe a noise gate here, maybe some suppression on the signal. And we plot all of these choices into the graph that you see there. And you can choose what is more important. Maybe for your application, false activation rate is really crucial, right? So you want to lower that. And OK, yeah, then it's going to reject a couple of things. Maybe you want to balance it out. So all of this you actually see, including the complete understanding of post-processing impact. And this is available for free for everyone on every audio project. Just click the performance calibration button in the dashboard. So yeah, recap of 27 seconds on the clock. Truly, what a year. Like, I think I speak for Zach as well, and for Dan and Matthijs, who were our first 2 employees, that we never imagined when we launched publicly in January 2020 that we'd have over 100,000 projects, 200 people in the room in California at a conference, so many amazing partners, so many customer stories actually here to share with you. Truly, truly amazing. Second, for you, some homework. Start thinking about your active learning strategy, right? And we can help. We have lots of experience doing that. And for us, the focus for 2023 is going to be around data, anomaly detection, and extensibility. And up to 1 million, want to go to 1 million developers. So with that, thank you all.